Good afternoon, everyone. I'm Claude Gustave, a senior student of the McCoy School of Engineering. And today my presentation is on slip-ring Cartridge valves and conventional spool valves. And basically it's a comparison between slip-ring Cartridge valves and conventional spool valves. And my mentor is Dr. Youngberg. Okay, so today we're going to be looking at the objectives and then a quick introduction on Cartridge valves and conventional spool valves. Then we're going to look at our methodology, a couple of results, a conclusion, my acknowledgement, and then my works cited. So the objective of our research was to compare the use of slip-ring Cartridge valves versus a conventional spool valve. So let's look at what a Cartridge valve is. So typically a Cartridge valve is a two-way valve. It's also referred to as a logic element. It comes in a variety of sizes, usually from 16 millimeters to 14 millimeters, and there's the standard 50, 63, and 100 millimeter. And the sizes refer to the orifice within the Cartridge valve, which I'll speak about a little later. Cartridge valves are normally used for directional pressure check and for flow control. So those are the three main purposes that people use Cartridge valves. And they're also built into a machine block, or also referred to as a manifold block. So the separate valves are fitted to just one big block. And ideally we use them for applications that require huge flow rates. And they're very good when it comes to preventing leaking. Okay, so here's a cross-sectional cutout of a Cartridge valve, and this is a hydraulic symbol. We have an A port and a B port, and where the spring touches the rectangular portion, it's referred to as an AP port. Now fluid can go through the AP port, through the B port, and also through the A port. If you look at the cross-sectional diagram, right here would be the orifice, and this is what determines the size of the Cartridge valve, the 16 to the 100 millimeter. This is the casing, and there's a poppet inside, and a spring, which allows the poppet to move up and down. So how a Cartridge valve works, we have something called closing forces and opening forces. And basically if the opening forces are greater than the closing forces, then the Cartridge valve will open up. And so the forces to close would be the spring force and the area of the AP, this area here, and pressure on the AP. So force is equal to pressure times area. So the pressure on the AP and the pressure and the area of the AP would give the force on the AP plus the spring force would equal to the closing force. And the opening force would be the pressure on the A port plus the area of the A port and plus the area of the B port times the pressure on the B port. And that would give the opening force. And so long as the opening force is greater than the closing force, then the valve is going to open. For Cartridge valves, there are different sizes. Other than the size, there are different areas. And so this one here is a 1 to 2 area Cartridge valve, meaning that the AP port is twice as big as the A port. So there's 1 to 2, there's also 1 to 1, and there's also 1 to 1.1. Okay, so I have a table which shows Cartridge valves and the respective, well, the maximum GPMs, the maximum amount of flow that could go through the Cartridge valves. The ISO and the DIN 2432 are just names to identify them easier. And so, as you see, as the size of the Cartridge valve increases, so does the maximum flow rate. Okay, so now let's look at conventional spool valves. And so for spool valves, they come in a number of different configurations, and The standards are two-way, two-position, three-way, two-position, four-way, two-position, and four-way, three-position. Now with the two-way, two-position, if you have a valve, it could move in two different positions, forward and back, and two-way meaning that fluid can go in two directions. And similarly with the four-way, three-position, you have the spool valve which could go in three positions. You could go either forward or backward, and fluid can go in four different ways. The spool within the spools are held by a pressure balance, and that's when the spring is de-energized. And if the spool valve is operated with a solenoid, then magnetic forces overcome the spring, which allow the spool valve to shift. It can also be operated manually with a lever. So I could use a lever to shift it to the different positions. And usually they're cheaper than Cartridge valves, which are built into a manifold block. And here I have a picture of a four-way, three-position, lever-operated directional control valve, which is the same thing as a spool valve. And this diagram here is the neutral position or the center position, and in this position no fluid is being moved. In this position, we shifted to the left. Fluid from the pressurized side is going to the A port, whichever port that be, and then fluids going from the B port back to a tank. And then in the bottom position, which is shifted to the left, is just the reverse of this one. So fluid is going from the A back to T, which is tank, and pressure is coming to the B port of whichever actuator we're using. So that was a brief summary of what Cartridge valves and what spool valves are. And so this is our methodology to compare them. We use a software called Automation Studio 6.1, and it's a simulation software. So what we did, we looked at a number of hydraulic applications. Actually, we looked at 5 of them. So we looked at a conventional basic hydraulic circuit, and with that, all it means is that we have an actuator, a cylinder, with a piston, and the piston extends and retracts. We also looked at a meter-in circuit. It's similar to the conventional, except that with the meter-in circuit, we could control how quickly the cylinder extends. Then we looked at a regenerative / conventional hydraulic circuit. It's still extension and retraction, but for the regenerative, we could control the speed. We could allow the cylinder to extend pretty quickly, and then turn it back to a conventional circuit where we allow it to extend a bit slower. And then we looked at a counterbalance circuit, which is usually used for press applications. So imagine a cylinder with a platen. The cylinder is about 270 degrees. It's facing down and has a platen attached to it. But the platen is extremely heavy, and so it could cause the cylinder to extend prematurely, which we don't want. We don't want that. So we use something called a counterbalance valve to prevent the platen from going down prematurely and to keep it suspended. And lastly, we looked at a sequencing circuit, and as the name suggests, it's sequencing. So we use 2 different actuators. We used a regular cylinder and a hydraulic motor. And how it worked was when the cylinder extended, when it fully extended, because of an increase in pressure, the motor would rotate. And so those were drawn with Automation Studio, and then we simulated them, and then we just compared them. And then we got a chance to do a cost analysis in just one of the circuits, which is the meter-in circuit. Okay, so I thought I'd start off with showing you the conventional hydraulic circuit, because this is like the basic hydraulic circuit, and from this other circuits have been developed. And as I said earlier, for the conventional hydraulic circuit, all it does is allow an actuator, which in our case is a cylinder, to extend and to retract. And so to the left I have a Cartridge valve solution, and to the right I have conventional spool valve solution. So this triangular portion here is my pump, and basically fluid goes to the different cartridge valves to allow the cylinder to extend and to retract. This is a spool valve. Spool valves are used in combination with cartridge valves. And so if I shift the spool to the A position, it's going to allow the cylinder to extend. And if I shift it to the B position, it's going to allow the cylinder to retract. This here is a electrical ladder which controls the directional control valves. And this here is a conventional spool valve. We just have the spool valve. And similarly, if I shift it to the A position, fluid pressure goes to the blind end side of the cylinder, and it pushes the cylinder. And if I want to retract the cylinder, then I just push it to the B position, which allows the cylinder to retract. And the electrical ladder is the same for both of them. And then this is the regenerator / conventional hydraulic circuit. For the cartridge valve solution, it uses two directional control valves. And if I activate the solenoid A and leave this in its regular position, it's going to allow the cylinder to extend pretty quickly to the middle. And then once it hits the middle, I'm going to switch it to allow it to return to a conventional. The reason for that is because let's say we're working on the workpiece would be in this section here. Now, I don't want it to, I want it to reach the workpiece very quickly, so I just make it go quickly, but it has little force. But once it reaches the workpiece, I want it to actually press the workpiece. And so I want to apply more force, I don't need as much speed. And so that's where the regenerative / conventional comes in. For regenerative, it goes pretty quickly, but once it reaches the workpiece, it goes conventional. It's a lot slower, but it gives more force, which is what we want. So this is the cartridge valve solution, and then this is the conventional spool valve solution. They both do the same thing, but one could be better than the other, depending on the application. So these are the results that we found out. So we found out that the cost of the cartridge valve solutions were considerably higher than spool valve solutions. That's because the cartridge valves are built into a manifold block, and it's a lot more expensive when it comes to machining those cartridge valves into the machine block. And with cartridge valve solutions, they require less conductors. So if I go back to the regenerator / conventional hydraulic circuit, it might seem a lot messy compared to the conventional spool valve solution, but as with any software, there's limitations, and as I said earlier, the cartridge valves are fit into a block, just one big block, and we couldn't do that with the software. So these, including this relief valve, would fit into just one block. And so that's where less conductors come in. We have so many conductors, like hoses here, hoses there, hoses there, but these will all be fit into just one big block. We also found out that for cartridge valves, they experience less pressure drops and thus less energy wastage compared to spool valves. And why is that? With spool valves, the fluid has to go over the spool, and so there's an increase in friction, and also with the more conductors, that also increases friction. And so there's a correlation between friction and pressure drops. With more friction, you have more pressure drop, and there's a correlation between pressure drop and horsepower. And so if you have more pressure drops, then you have wastage of more power. When you compare it to a spool valve, to a cartridge valve simply open up and close. And since there's less conductors, there's also less friction. And so with less friction, there's less pressure drops, and with less pressure drops, you have less wastage of power. Also with cartridge valves, we have less chances of leakage. And cartridge valves are a lot easier to troubleshoot and to maintain compared to conventional spool valves. And we've also found that cartridge valves are very tolerant to dirt compared to spool valves. Okay, so this is a bill of material comparison for the meter in circuit. And they both use the same components. Same hydraulic reservoir, same check valve, same relief valve, same filter, same electric motor. But the differentiating cost was the cost of the manifold. That added at least $2,000 that added at least $2,000 more to the actual cost, which made the cartridge valve solution a lot more expensive than the spool valve solution. So my conclusion was, our conclusion was that for every application, it should be analyzed on its own merits, and it also depends on what the manufacturer, the person who intends to use those, what they actually want. If they're trying to be economical, then we would suggest that they go with the cartridge valves, because in the long run they save a lot more money. But if they want to, I mean, they can still go ahead with the spool valves, but it would be more costly in the long run. And as I said, it all depends on the application.